Welcome, lovely viewers, to another exciting video. Hello, dear viewers. Get ready to expand your horizons as we delve into Jurassic. The Jurassic is a geologic period and stratigraphic system that spanned from the end of the Triassic Period million years ago to the beginning of the Cretaceous Period, approximately The Jurassic constitutes the middle period of the Mesozoic Era as well as the 8th period of the Phanerozoic Eon and is named after the Jura Mountains, where limestone strata from the period were first identified. The start of the Jurassic was marked by the major Triassic-Jurassic extinction event, associated with the eruption of the Central Atlantic Magmatic Province (CAMP). The beginning of the Toarcian Age started around 183 million years ago and is marked by the Toarcian Oceanic Anoxic Event, a global episode of oceanic anoxia, ocean acidification, and elevated global temperatures associated with extinctions, likely caused by the eruption of the Karoo-Ferrar large igneous provinces. The end of the Jurassic, however, has no clear, definitive boundary with the Cretaceous and is the only boundary between geological periods to remain formally undefined. By the beginning of the Jurassic, the supercontinent Pangaea had begun rifting into two landmasses, Laurasia to the north and Gondwana to the south. The climate of the Jurassic was warmer than the present, and there were no ice caps. Forests grew close to the poles, with large arid expanses in the lower latitudes. On land, the fauna transitioned from the Triassic fauna, dominated jointly by dinosaur mammals and Toarcian archosaurs, to one dominated by dinosaurs alone. The first stem group birds appeared during the Jurassic, evolving from a branch of theropod dinosaurs. Other major events include the appearance of the earliest crabs and modern frogs, salamanders and lizards. Mammaliformes, one of the few cynodont lineages to survive the end of the Triassic, continued to diversify throughout the period, with the Jurassic seeing the emergence of the first crown group mammals. Crocodilomorphs made the transition from a terrestrial to an aquatic life. The oceans were inhabited by marine reptiles such as ichthyosaurs and plesiosaurs, while pterosaurs were the dominant flying vertebrates. Modern sharks and rays first appeared and diversified during the period, while the first known crown group telest fish appeared near the end of the period. The flora was dominated by ferns and gymnosperms, including conifers, of which many modern groups made their first appearance during the period, as well as other groups like the extinct bennettitals. As we transition, let's shed light on etymology and history and its relevance to our ongoing exploration. The chronostratigraphic term Jurassic is linked to the Jura Mountains, a forested mountain range that mainly follows the France-Switzerland border. The name Jura is derived from the Celtic root vir Gaulish Juras, wooded mountain, which was borrowed into Latin as a name of a place and evolved into Juria and finally Jura. During a tour of the region in 1795, German naturalist Alexander von Humboldt recognized carbonate deposits within the Jura Mountains as geologically distinct from the Triassic-aged Muschelkalk of southern Germany, but he erroneously concluded that they were older. He then named them Jura limestone in 1799. In 1829, the French naturalist Alexandre Brongniart published a book entitled Description of the Terrains that Constitute the Crust of the Earth, or Essay on the Structure of the Known Lands of the Earth. In this book, Brongniart used the phrase terrains Jurassicus when correlating the Jura kalkstein of Humboldt with similarly aged Oolitic limestones in Britain, thus coining and publishing the term Jurassic. The German geologist Leopold von Buch in 1839 established the threefold division of the Jurassic, originally named from oldest to the youngest, the Black Jurassic, Brown Jurassic, and White Jurassic. The term Lias had previously been used for strata of equivalent age to the Black Jurassic in England by William Knebia and William Phillips in 1822. William Phillips, the geologist, worked with William Knebia to find out more about the Black Jurassic in England. The French paleontologist Alcide Zorbigny in papers between 1842 and 1852 divided the Jurassic into 10 stages based on ammonite and other fossil assemblages in England and France, of which 7 are still used, but none has retained its original definition. The German geologist and paleontologist Friedrich August von Quenstedt in 1858 divided the three series of von Buch in the Swabian Jura into 6 subdivisions defined by ammonites and other fossils. The German paleontologist Albert Oppel in his studies between 1856 and 1858 altered Zorbigny's original scheme and further subdivided the stages into biostratigraphic zones, based primarily on ammonites. Most of the modern stages of the Jurassic were formalized at the Karoo-Ferrar Luxembourg in 1962. Now, we shift our focus to geology, a topic that deserves our attention. The Jurassic period is divided into 3 epochs: early, middle, and late. Similarly, in stratigraphy, the Jurassic is divided into the Lower Jurassic, Middle Jurassic, and Upper Jurassic series. Geologists divide the rocks of the Jurassic into a stratigraphic set of units called stages, each formed during corresponding time intervals called ages. Stages can be defined globally or regionally. For global stratigraphic correlation, the International Commission on Stratigraphy (ICS) ratified global stages based on a global boundary stratotype section and point GSSP from a single formation, a stratotype identifying the lower boundary of the stage. The ages of the Jurassic from youngest to oldest are as follows. Series epoch stage lower boundary early Cretaceous variation near rust and styler background color. Upper late Jurassic Tithanian 149.20.7 near Kimmeridgian 154.80.8 near Oxfordian 161.51 near rust and styler background color. Middle Jurassic Calovian 165.31.1 near Bathanian 168.21.2 near Bogosian 170.90.8 near Olenian 174.70.8 near rust and styler background color. Out early Jurassic Toarcian 184.20.3 near Plians Bacchian 192.90.3 near Silurian 199.50.3 near Hettangian 201.40.2 near. As we enter this new chapter, let's navigate the complexities of stratigraphy and unravel its multifaceted nature. Jurassic stratigraphy is primarily based on the use of ammonites as index fossils. The first appearance datum of specific ammonite taxa is used to mark the beginnings of stages, as well as smaller timespans within stages, referred to as ammonite zones. These, in turn, are also sometimes subdivided further into subzones. Global stratigraphy is based on standard European ammonite zones, with other regions being calibrated to the European successions. Let's now shift gears and explore early Jurassic through a critical lens, uncovering its strengths and weaknesses. The oldest part of the Jurassic period has historically been referred to as the Lias or Liassic, roughly equivalent in extent to the early Jurassic, but also including part of the preceding Haitian. The Hettangian stage was named by Swiss paleontologist Jung Renevier in 1864 after Hettange in northeastern France. The GSSP for the base of the Hettangian is located at the Kuyok Pass, Jura Mountains, northern Calcareous Alps, Austria. It was ratified in 2010. The beginning of the Hettangian, and thus the Jurassic as a whole, is marked by the first appearance of the ammonite Silicious speleotherolicum in the Kendelbach Formation exposed at Kuyok. The base of the Jurassic was previously defined as the first appearance of Silicious planorbis by Albert Oppel in, but this was changed as the appearance was seen as too localist an event for an international boundary. The Silurian stage was first defined and introduced into scientific literature by Alcide Zorbigny in 1842. It takes its name from the French town Semur-en-Oise, near Dijon. The original definition of Silurian included what is now the Hettangian. The GSSP of the Silurian is located at a cliff face north of the hamlet of East Quantoxhead, 6 kilometers east of Watchet, Somerset, England, within the Blue Lias, and was ratified in 2000. The beginning of the Silurian is defined by the first appearance of the ammonite Vermicras quantoxans. Albert Oppel in 1858 named the Pliensbachian stage after the hamlet of Pliensbach in the community of Zell unter Hechelberg in the Swabian Alb, near Stuttgart, Germany. The GSSP for the base of the Pliensbachian is found at the Winehaven locality in Robin Hood's Bay, Yorkshire, England, in the Redcomb Mudstone Formation, and was ratified in 2005. The beginning of the Pliensbachian is defined by the first appearance of the ammonite Bifrosaurus donovani. The village Thouars Latin, Toarcian, just south of Somme in the Loire Valley of France, lends its name to the Toarcian stage. The Toarcian was named by Alcide Sorbigny in 1842, with the original locality being Vriens Quarry around to northwest of Thouars. The GSSP for the base of the Toarcian is located at Peniche, Portugal, and was ratified in 2014. The boundary is defined by the first appearance of ammonites belonging to the subgenus Dactyliceros odactylites. In this section, we'll be deep diving into Middle Jurassic, unraveling its complexities and uncovering valuable insights. The Ollinian is named after the city of Olin in Germany. The Ollinian was defined by Swiss geologist Karl Mayer-Eimer in 1864. The lower boundary was originally between the dark clays of the Black Jurassic and the overlying clay sandstone and ferruginous oolite of the Brown Jurassic sequences of southwestern Germany. The GSSP for the base of the Ollinian is located at Fuentealces in the Iberian Range near Guadalajara, Spain, and was ratified in 2000. The base of the Ollinian is defined by the first appearance of the ammonite Lysarosepolinum. Alcide Sorbigny in 1842 named the Bojocian stage after the town of Bayeux Latin, Bojos in Normandy, France. The GSSP for the base of the Bojocian is located in the Martin-Hires section at Cabo Mondigo, Portugal. It was ratified in 1997. The base of the Bojocian is defined by the first appearance of the ammonite Hyperlysaros mundum. The Bathanian is named after the city of Bath, England, introduced by Belgian geologist Dumoulin de Holle in 1843, after an incomplete section of oolitic limestones in several quarries in the region. The GSSP for the base of the Bathanian is Ravin-Doubs, as Oran area, Alpes de Haute Provence, France. It was ratified in 2009. The base of the Bathanian is defined by the first appearance of the ammonite Gonokitz convergens at the base of the Zigzagosaurus zigzag ammonite zone. The Calovian is derived from the Latinized name of the village of Kelways in Wiltshire, England, and was named by Alcide Sorbigny in 1852, originally the base at the contact between the Forest Marble Formation and the Cornbrash Formation. However, this boundary was later found to be within the upper part of the Bathanian. The base of the Calovian does not yet have a certified GSSP. The working definition for the base of the Calovian is the first appearance of ammonites belonging to the genus Keplerites. Prepare yourself for an eye-opening discussion on late Jurassic in the upcoming portion of this video. The Oxfordian is named after the city of Oxford in England and was named by Alcide Sorbigny in 1844 in reference to the Oxford clay. The base of the Oxfordian lacks a defined GSSP. W. J. Arkell in studies in 1939 and 1946 placed the lower boundary of the Oxfordian as the first appearance of the ammonite Quenstatosaurus murray, then placed in the genus Vertumnisaurus. Subsequent proposals have suggested the first appearance of Cardiosaurus redglyphants as the lower boundary. The village of Kimmeridge on the coast of Dorset, England, is the origin of the name of the Kimmeridgian. The stage was named by Alcide Sorbigny in 1842 in reference to the Kimmeridge clay. The GSSP for the base of the Kimmeridgian is the Floddigary section at Stuffin Bay on the Isle of Skye, Scotland, which was ratified in 2021. The boundary is defined by the first appearance of ammonites marking the Boral-Bohini zone and the Subral-Bailey zone. The Tithanian was introduced in scientific literature by Albert Oppel in 1865. The name Tithanian is unusual in geological stage names because it is derived from Greek mythology rather than a place name. Tithonus was the son of Laman of Troy and fell in love with Eos, the Greek goddess of dawn. His name was chosen by Albert Oppel for this stratigraphical stage because the Tithonian finds itself hand in hand with the dawn of the Cretaceous. The base of the Tithonian currently lacks a GSSP. The working definition for the base of the Tithonian is the first appearance of the ammonite genus Gravesia. The upper boundary of the Jurassic is currently undefined, and the Jurassic-Cretaceous boundary is currently the only system boundary to lack a defined GSSP. Placing a GSSP for this boundary has been difficult because of the strong regionality of most biostratigraphic markers and lack of any chemostratigraphic events, such as isotope excursions, large sudden changes in ratios of isotopes, that could be used to define or correlate a boundary. Calpionalids, an enigmatic group of planktonic protists with urn-shaped calcitic tests briefly abundant during the latest Jurassic to earliest Cretaceous, have been suggested to represent the most promising candidates for fixing the Jurassic-Cretaceous boundary, in particular, the first appearance Calpionella alpina, coinciding with the base of the eponymous alpine subzone, has been proposed as the definition of the base of the Cretaceous. The working definition for the boundary has often been placed as the first appearance of the ammonite Stramagella kirby, formerly placed in the genus Bariacella, but its use as a stratigraphic indicator has been questioned, as its first appearance does not correlate with that of Celsius alpina. In this segment, we'll be unraveling the complexities of mineral and hydrocarbon deposits and exploring its multifaceted nature. The Kimmeridge clay and equivalents are the major source rock for the North Sea oil. The Arabian intrashelf basin, deposited during the Middle and Late Jurassic, is the setting of the world's largest oil reserves, including the Gower Field, the world's largest oil field. The Jurassic-aged Sargu and Naklekim formations are major source rocks for oil in Iraq. Over 1,500 gigatons of Jurassic coal reserves are found in northwest China, primarily in the Turpanhami Basin and the Ordos Basin. Brace yourself for an enlightening exploration of impact structures as we dive into its profound implications. Major impact structures include the Morocquing impact structure, a 70-km diameter impact structure buried beneath the Kalahari Desert in northern South Africa. The impact is dated to the Tithonian, approximately 146.060.16 m. Another major structure is the Puches-Katunki crater, 40 km in diameter, buried beneath Nizhny Novgorod Oblast in western Russia. The impact has been dated to the Silurian, 195.91 m. Now, let's shift our focus to paleogeography and tectonics and embark on an intellectual exploration of its various dimensions. At the beginning of the Jurassic, all of the world's major landmasses were coalesced into the supercontinent Pango, which during the early Jurassic began to break up into northern supercontinent Laurasia and the southern supercontinent Gondwana. The rifting between North America and Africa was the first to initiate, beginning in the early Jurassic, associated with the emplacement of the Central Atlantic Magmatic Province. During the Jurassic, the North Atlantic Ocean remained relatively narrow, while the South Atlantic did not open until the Cretaceous. The continents were surrounded by Panthalassa, with the Tethys Ocean between Gondwana and Asia. At the end of the Triassic, there was a marine transgression in Europe, flooding most parts of Central and Western Europe, transforming it into an archipelago of islands surrounded by shallow seas. During the Jurassic, both the North and South Pole were covered by oceans. Beginning in the early Jurassic, the Boreal Ocean was connected to the Proto-Atlantic by the Viking Corridor or Transcontinental Lauragin Seaway, a passage between the Baltic Shield and Greenland several hundred kilometers wide. During the Calovian, the Turgay Epicontinental Sea formed, creating a marine barrier between Europe and Asia. Madagascar and Antarctica began to rift away from Africa during the late early Jurassic in association with the eruption of the Karoo-Ferrar large igneous provinces, opening the western Indian Ocean and beginning the fragmentation of Gondwana. At the beginning of the Jurassic, North and South America remained connected, but by the beginning of the late Jurassic they had rifted apart to form the Caribbean Seaway, also known as the Hispanic Corridor, which connected the North Atlantic Ocean with eastern Panthalassa. Paleontological data suggest that the seaway had been open since the early Jurassic. As part of the Nevadan orogeny, which began during the Triassic, the Cache Creek Ocean closed, and various terranes including the large Wrangellia terrane accreted onto the western margin of North America. By the Middle Jurassic, the Siberian Plate and the North China Amur block had collided, resulting in the closure of the Mongol-Okhotsk Ocean. During the early Jurassic, around 190 million years ago, the Pacific Plate originated at the triple junction of the Farallon, Phoenix, and Izenergy tectonic plates, the three main oceanic plates of Panthalassa. The previously stable triple junction had converted to an unstable arrangement surrounded on all sides by transform faults because of a kink in one of the plate boundaries, resulting in the formation of the Pacific Plate at the center of the junction. During the Middle to early late Jurassic, the Sundance Seaway, a shallow epicontinental sea, covered much of northwest North America. Eustatic sea level is estimated to have been close to present levels during the Hettangian and Silurian, rising several tens of meters during the late Silurian Pliensbachian before regressing to near present levels by the late Pliensbachian. There seems to have been a gradual rise to a peak of meters above present sea level during the Toarcian. During the latest part of the Toarcian, the sea level again dropped by several tens of meters. It progressively rose from the Oolian onwards, aside from dips of a few tens of meters in the Bogotian and around the Calovian-Oxfordian boundary, peaking possibly as high as 140 meters above present sea level at the Kimmeridgian-Tithonian boundary. The sea levels falls in the late Tithonian, perhaps to around 100 meters, before rebounding to around 110 meters at the Tithonian variation boundary. The sea level within the long-term trends across the Jurassic was cyclical, with 64 fluctuations, 15 of which were over 75 meters. The most noted cyclicity in Jurassic rocks is fourth order, with a periodicity of approximately 410,000 years. During the early Jurassic, the world's oceans transitioned from an aragonite sea to a calcite sea chemistry, favoring the dissolution of aragonite and precipitation of calcite. The rise of calcareous plankton during the Middle Jurassic profoundly altered ocean chemistry, with the deposition of bimineralized plankton on the ocean floor acting as a buffer against large co-emissions. As we progress through this video, let's shift our attention towards climate and uncover its hidden depths. The climate of the Jurassic was generally warmer than that of present, by around 5, with atmospheric carbon dioxide likely about 4 times higher. Intermittent cold snap intervals are known to have occurred during this time period, however, interrupting the otherwise warm greenhouse climate. Forests likely grew near the poles, where they experienced warm summers and cold, sometimes snowy winters. There were unlikely to have been ice sheets given the high summer temperatures that prevented the accumulation of snow, though there may have been mountain glaciers. Dripstones and glendonites in northeastern Siberia during the early to middle Jurassic indicate cold winters. The ocean depths were likely 8 sea change warmer than present, and coral reefs grew of latitude further north and south. The intertropical convergence zone likely existed over the oceans, resulting in large areas of desert and scrubland in the lower latitudes between north and south of the equator. Tropical rainforest and tundra biomes are likely to have been rare or absent. The Jurassic also witnessed the decline of the Pangan megamonsoon that had characterized the preceding Permian and Triassic periods. Variation in the frequency of wildfire activity in the Jurassic was governed by the 405-year eccentricity cycle. Thanks to the breakup of Pango, the hydrological cycle during the Jurassic was significantly enhanced. The beginning of the Jurassic was likely marked by a thermal spike corresponding to the Triassic-Jurassic extinction and eruption of the Central Atlantic Magmatic Province. The first part of the Jurassic was marked by the early Jurassic cool interval between 199 and 183 million years ago. It has been proposed that glaciation was present in the northern hemisphere during both the early Pliensbachian and the latest Pliensbachian. There was a spike in global temperatures of around 4 during the early part of the Toarcian, corresponding to the Toarcian Oceanic Anoxic Event and the eruption of the Karoo-Ferrar large igneous provinces in southern Gondwana, with the warm interval extending to the end of the Toarcian around 174 million years ago. During the Toarcian warm interval, ocean surface temperatures likely exceeded 30 C, and equatorial and subtropical ERNS regions are likely to have been extremely arid, with temperatures in the interior of Pangaea likely in excess of 40. Its Toarcian warm interval is followed by the Middle Jurassic cool interval MJCI between 174 and 164 million years ago, which may have been punctuated by brief, ephemeral ice intervals. During the Oligocene, precessionally forced climatic changes dictated peatland wildfire magnitude and frequency. The European climate appears to have become noticeably more humid at the Oligocene-Bogocean boundary, but then became more arid during the Middle Bogocean. A transient ice age possibly occurred in the late Bogocean. The Carovian-Oxfordian boundary at the end of the MJCI witnessed particularly notable global cooling, potentially even an ice age. This is followed by the Kimmeridgian warm interval KWI between 164 and 150 million years ago. Based on fossil wood distribution, this was one of the wettest intervals of the Jurassic. The Pangaean interior had less severe seasonal swings than in previous warm periods, as the expansion of the Central Atlantic and Western Indian Ocean provided new sources of moisture. A prominent drop in temperatures occurred during the Tithonian, known as the Early Tithonian Cooling Event ETCE. The end of the Jurassic was marked by the Tithonian Early Beremian Cool Interval TBCI, beginning 150 million years ago and continuing into the early Cretaceous. Welcome to the next segment, where we explore Toarcian Oceanic Anoxic Event and its significance in our journey. The Toarcian Oceanic Anoxic Event (TOAE), also known as the Jenkins Event, was an episode of widespread oceanic anoxia during the early part of the Toarcian Age, c. 183 MIA. It is marked by a globally documented high-amplitude negative carbon isotope excursion, as well as the deposition of black shales and the extinction and collapse of carbonate-producing marine organisms, associated with a major rise in global temperatures. The TOAE is often attributed to the eruption of the Karoo-Ferrar large igneous provinces and the associated increase of carbon dioxide concentration in the atmosphere, as well as the possible associated release of methane clathrates. This likely accelerated the hydrological cycle and increased silicate weathering, as evidenced by an increased amount of organic matter of terrestrial origin found in marine deposits during the TOAE. Groups affected include ammonites, ostracids, foraminifera, bivalves, anidarians, and especially brachiopods, for which the TOAE represented one of the most severe extinctions in their evolutionary history. While the event had significant impact on marine invertebrates, it had little effect on marine reptiles. During the TOAE, the Sichuan Basin was transformed into a giant lake, probably 3 times the size of modern-day Lake Superior, represented by the Daonshe member of the Zhejiang Formation. The lake likely sequestered gigatons of organic carbon and inorganic carbon during the event. Seawater, which had already substantially decreased prior to the event, increased slightly during the early stages of the TOAE, before dropping to its lowest point around the middle of the event. This ocean acidification is the probable cause of the collapse of carbonate production. Additionally, anoxic conditions were exacerbated by enhanced recycling of phosphorus back into ocean water as a result of high ocean acidity and temperature inhibiting its mineralization into apatite. The abundance of phosphorus in marine environments caused further eutrophication and consequent anoxia in a positive feedback loop. As we enter this new phase, let's uncover the impact of End-Jurassic transition on our broader topic. The End-Jurassic transition was originally considered one of 8 mass extinctions, but is now considered to be a complex interval of faunal turnover, with the increase in diversity of some groups and decline in others, though the evidence for this is primarily European. probably controlled by changes in eustatic sea level. Get ready to immerse yourself in the world of end-Triassic extinction as we examine its impact and relevance. There is no evidence of a mass extinction of plants at the Triassic-Jurassic boundary. At the Triassic-Jurassic boundary in Greenland, the sporomorph pollen and spores record suggests a complete floral turnover. An analysis of macrofossil floral communities in Europe suggests that changes were mainly due to local ecological succession. At the end of the Triassic, the Peltospermaceae became extinct in most parts of the world, with Lepidopteras persisting into the early Jurassic in Patagonia. Dicroidium, a Corystisperm seed fern that was a dominant part of Gondwanan floral communities during the Triassic, also declined at the Triassic-Jurassic boundary, surviving as a relict in Antarctica into the early Jurassic. In the next portion, we'll be immersing ourselves in the realm of conifers and examining its broader implications. Conifers formed a dominant component of Jurassic floras. The late Triassic and Jurassic was a major time of diversification of conifers, with most modern conifer groups appearing in the fossil record by the end of the Jurassic, having evolved from Voltzian ancestors. Araucarian conifers have their first unambiguous records during the early Jurassic, and members of the modern genus Araucaria were widespread across both hemispheres by the Middle Jurassic. Also abundant during the Jurassic is the extinct family Chirolepidaceae, often recognized through their highly distinctive Classopolis pollen. Jurassic representatives include the pollen cone Classostrobus and the seed cone Araucaria. Araucarian and Chirolepidaceae conifers often occur in association. The oldest definitive record of the cypress family Cupressaceae is a Strahamia minuta from the early Jurassic Plians Bacchian of Patagonia, known from many parts of the plant. The reproductive structures of a Strahamia have strong similarities to those of the primitive living cypress genera Taiwania and Cunninghamia. By the middle to late Jurassic, Cupressaceae were abundant in warm temperate tropical regions of the northern hemisphere, most abundantly represented by the genus Elatids. The Jurassic also saw the first appearances of some modern genera of cypresses, such as Sequoia. Members of the extinct genus Schizollepidopsis, which likely represent a stem group to the pine family Pinaceae, were widely distributed across Eurasia during the Jurassic. The oldest unambiguous record of Pinaceae is the pine cone Ethistrobus, known from the late Jurassic Kimmeridgian of Scotland, which remains the only known unequivocal fossil of the group before the Cretaceous. Despite being the earliest known member of the Pinaceae, Ethistrobus appears to be a member of the pinoid clade of the family, suggesting that the initial diversification of Pinaceae occurred earlier than has been found in the fossil record. The earliest record of the U-family Taxaceae is Palotaxus rediviva, from the Hettangian of Sweden, suggested to be closely related to the living Estrataxus, while Marsky Jurassica from the Middle Jurassic of Yorkshire, England, and material from the Calovian Oxfordian Dagobed in China are thought to be closely related to Amentaxus, with the latter material assigned to the modern genus, indicating that Taxaceae had substantially diversified by the end of the Jurassic. The oldest unambiguous members of Podocarpaceae are known from the Jurassic, found across both hemispheres, including Scarbadia and Heresicoppus from the Middle Jurassic of England, as well as unnamed species from the Middle-Late Jurassic of Patagonia. During the early Jurassic, the flora of the mid-latitudes of eastern Asia were dominated by the extinct deciduous broad-leafed conifer Podosomids, which appears to not be closely related to any living family of conifer. Its range extended northwards into polar latitudes of Siberia and then contracted northward in the middle to late Jurassic, corresponding to the increasing aridity of the region. As we enter this new phase, let's navigate the complexities of ginkgos and discover its practical applications. Ginkgos, of which the sole living species is Ginkgo biloba, were more diverse during the Jurassic. They were among the most important components of Eurasian Jurassic floras and were adapted to a wide variety of climatic conditions. The earliest representatives of the genus Ginkgo, represented by ovulate and pollen organs similar to those of the modern species, are known from the Middle Jurassic in the Northern Hemisphere. Several other lineages of ginkgolans are known from Jurassic rocks, including Eumea, Crenina, Nagrinia, and Carcinia. These lineages are associated with ginkgo-like leaves, but are distinguished from living and fossil representatives of ginkgo by having differently arranged reproductive structures. Eumoltulpus from the Jurassic of Asia has strap-shaped ginkgo-like leaves with highly distinct reproductive structures with similarities to those of Peltaspum and Corystaspum seed ferns, has been suggested to be a member of Ginkgo's sensulotto. In this chapter, we'll be unraveling the enigma of Bennettitals and discovering its transformative power. Thumb uprighter restoration of a member of Bennettitals belonging to Williamsoniaceae. Bennettitals, having first become widespread during the preceding Triassic, were diverse and abundant members of Jurassic floras across both hemispheres. The foliage of Bennettitals bears strong similarities to those of cycads, to such a degree that they cannot be reliably distinguished on the basis of morphology alone. Leaves of Bennettitals can be distinguished from those of cycads their different arrangement of stomata, and the two groups are not thought to be closely related. Jurassic Bennettitals predominantly belong to the group Williamsoniaceae, which grew as shrubs and small trees. The Williamsoniaceae are thought to have had a divaricate branching habit, similar to that of living Banksia, and adapted to growing in open habitats with poor soil nutrient conditions. Bennettitals exhibit complex, flower-like reproductive structures, some of which are thought to have been pollinated by insects. Several groups of insects that bear long proboscis, including extinct families such as calligrammatid lacewings and extant ones such as icrosaurid flies, are suggested to have been pollinators of Bennettitals, feeding on nectar produced by Bennettitalian cones. Without wasting any more time, let's jump into the fascinating world of cycads. Cycads reached their apex of diversity during the Jurassic and Cretaceous periods. Despite the Mesozoic sometimes being called the Age of Cycads, cycads are thought to have been a relatively minor component of mid-Mesozoic floras, with the Bennettitals and Nilsoniales, which have cycad-like foliage, being dominant. The Nilsoniales have often been considered cycads or cycad relatives, but have been found to be distinct on chemical grounds, and perhaps more closely allied with Bennettitals. The relationships of most Mesozoic cycads to living groups are ambiguous, with no Jurassic cycads belonging to either of the two modern groups of cycads, though some Jurassic cycads possibly represent stem group relatives of modern Cycadaceae, like the leaf genus Parasicas known in Europe, and Zamiaceae, like some European species of the leaf genus Pseudotenis. Also widespread during the Jurassic was the extinct Ctenis lineage, which appears to be distantly related to modern cycads. Modern cycads are pollinated by beetles, and such an association is thought to have formed by the early Jurassic. In the upcoming section, we'll be dissecting other seed plants and exploring its intricate connections to our topic. Although there have been several claimed records, there are no widely accepted Jurassic fossil records of flowering plants, which make up 90% of living plant species, and fossil evidence suggests that the group diversified during the following Cretaceous. The earliest known Nettophytes, one of the four main living groups of gymnosperms, appeared by the end of the Jurassic, with the oldest unequivocal Nettophyte being the seed Daviltia from the late Jurassic of North America. Seed ferns. Pteridospermatophyta is a collective term to refer to disparate lineages of fern-like plants that produce seeds but have uncertain affinities to living seed plant groups. A prominent group of Jurassic seed ferns is the Cotoneales, which reached their zenith during the Jurassic, with widespread records in the northern hemisphere, though records in the southern hemisphere remain rare. Due to their berry-like seed-bearing capsules, they have often been suggested to have been closely related or perhaps ancestral to flowering plants, but the evidence for this is inconclusive. Corystaspum-aligned seed ferns, such as Pachypteris and Comlepteris, were widespread across both hemispheres during the Jurassic. Trichanoscales, also known as leptostrobils, are a group of seed plants and certain affinities with persistent heavily dissected leaves borne on deciduous short shoots subtended by scale-like leaves, known from the late Triassic, possibly late Permian to Cretaceous. They are thought to have had a tree or shrub-like habit and formed a conspicuous component of northern hemisphere Mesozoic temperate and warm temperate floras. The genus Phanerozoic was widespread in early Middle Jurassic floras of eastern Asia and Siberia. The pentaxylals, a small but clearly distinct group of Leona-like seed plants of obscure affinities, first appeared during the Jurassic. Their distribution appears to have been confined to eastern Gondwana. Let's zoom in on ferns and allies and understand its implications. Living families of ferns widespread during the Jurassic include Dipterodaceae, Metoniaceae, Gleicheniaceae, Oshundaceae and Maratiaceae. Polypodials, which make up 80% of living fern diversity, have no record from the Jurassic and are thought to have diversified in the Cretaceous, though the widespread Jurassic herbaceous fern genus Coleopteris, historically interpreted as a close relative of tree ferns of the family Dixoniaceae, has recently been reinterpreted as an early relative of the group. The Ciaphales, the group containing most modern tree ferns, appeared during the late Jurassic, represented by members of the genus Ciaphicalis, which are suggested to be early members of Ciaphicae on the basis of cladistic analysis. Only a handful of possible records exist of the Hymenophyllaceae from the Jurassic, including Hymenophyllite macrosporangiatus from the Russian Jurassic. The oldest remains of modern horsetails of the genus Equisetum first appear in the early Jurassic, represented by Equisetum dimorphum from the early Jurassic of Patagonia and Equisetum lateral from the early to middle Jurassic of Australia. Silicified remains of Equisetum thermal from the late Jurassic of Argentina exhibit all the morphological characters of modern members of the genus. The estimated split between Equisetum boditans and all other living Equisetum is estimated to have occurred no later than the early Jurassic. Get ready for a thought-provoking discussion as we delve into lower plants and its impact on our understanding. Quartz virtually identical to modern species are known from the Jurassic onwards. Sotis rowandi from the Middle Jurassic of Oregon is the earliest known species to represent all major morphological features of modern Isotis. More primitive forms such as Narthastina, which retain an elongated stem, persisted into the early Cretaceous. The Moscoindebrium from the Middle Jurassic of Russia, which was found associated with dinosaur bones, is thought to be related to the Splitchnaceae, which grow on animal carcasses. Brachyuchlinia from the same region is thought to be related to dicronals. Hymrixela from the Jurassic of Patagonia is thought to belong to either Polytrichaceae or Timulaceae. The liverwort pellets hamiensis from the Middle Jurassic Sissionia Formation of China is the oldest record of the family Peliaceae. Palaviciniates sandalinensis from the same deposit is thought to belong to the subclass Palavicinianae within the Palavicinials. Richardsis sandalinensis, also from the same deposit, is the only Jurassic record of Rixiaceae. Now, let's redirect our focus towards crocodilomorphs and discover its significance in our narrative. The Triassic-Jurassic extinction decimated Pseudochean diversity, with crocodilomorphs, which originated during the early-late Triassic, being the only group of Pseudocheans to survive. All other Pseudocheans, including the herbivorous Aetosaurs and carnivorous Rauisuchians, became extinct. The morphological diversity of crocodilomorphs during the early Jurassic was around the same as that of late Triassic Pseudocheans, but they occupied different areas of morphospace, suggesting that they occupied different ecological niches to their Triassic counterparts and that there was an extensive and rapid radiation of crocodilomorphs during this interval. While living crocodilians are mostly confined to an aquatic ambush predator lifestyle, Jurassic crocodilomorphs exhibited a wide variety of life habits. An unnamed protosuchid known from teeth from the early Jurassic of Arizona represents the earliest known herbivorous crocodilomorph, an adaptation that appeared several times during the Mesozoic. The Thalattosuchia, a clade of predominantly marine crocodilomorphs, first appeared during the early Jurassic and became a prominent part of marine ecosystems. Within Thalattosuchia, the Metriahinchidae became highly adapted for life in the open ocean, including the transformation of limbs into flippers, the development of a tail fluke, and smooth, skull-less skin. The morphological diversity of crocodilomorphs during the early and middle Jurassic was relatively low compared to that in later time periods and was dominated by terrestrial small-bodied, long-legged Sphenocheans, early crocodiliforms and Thalattosuchians. The Nugia, a major group of crocodilomorphs, first appeared during the early to middle Jurassic. The Nugia represents the transition from an ancestrally terrestrial lifestyle to a freshwater aquatic ecology similar to that occupied by modern crocodilians. The timing of the origin of Nugia is disputed. The oldest record of Nugians has been suggested to be Calcoiacus from the early Jurassic of Arizona, which in many analyses has been recovered as the earliest branching member of the Nugian family Goniophylidae, which radically alters times of diversification for crocodilomorphs. However, this placement has been disputed, with some analyses finding it outside Nugia, which would place the oldest records of Nugia in the Middle Jurassic. Razan and Drongobe from the Middle Jurassic of Madagascar has been suggested to represent the oldest record of Notosuchia, a primarily Gondwan and clade of mostly terrestrial crocodilomorphs, otherwise known from the Cretaceous and Cenozoic. As we enter this new phase, let's navigate the complexities of turtles and discover its practical applications. Stem group turtles Testudinata diversified during the Jurassic. Jurassic stem turtles belong to two progressively more advanced clades, the Mesocalidia and Parachalidia. It is thought that the ancestral condition for Mesocalidians is aquatic, as opposed to terrestrial for Testudinatus. The two modern groups of turtles, Testudines, Pluridira and Cryptodira, diverged by the beginning of the late Jurassic. The oldest known Pluridias, the Platycalidae, are known from the late Jurassic of Europe and the Americas, while the oldest unambiguous Cryptodia, Cenospideritis, an early relative of softshell turtles, is known from the late Jurassic of China. The Thalassocalidia, a diverse lineage of marine turtles unrelated to modern sea turtles, are known from the late Jurassic of Europe and South America. Let's now venture into the realm of Lepidopteros and explore the fascinating intricacies it holds. Brachiocephalians, the sole living representative being the Chotara, had achieved a global distribution by the beginning of the Jurassic, and represented the dominant group of small reptiles during the Jurassic globally. Brachiocephalians reached their highest morphological diversity in their evolutionary history during the Jurassic, occupying a wide range of lifestyles, including the aquatic pleurosaurs with long snake-like bodies and reduced limbs, the specialized herbivorous Iolenodontids, as well as the Saphosaurs, which had broad tooth plates indicative of durophagy. Brachiocephalians disappeared from Asia after the early Jurassic. The last common ancestor of living squamates, which includes lizards and snakes, is estimated to have lived around 190 million years ago during the early Jurassic, with the major divergences between modern squamate lineages estimated to have occurred during the early to middle Jurassic. Squamates first appear in the fossil record during the middle Jurassic, including members of modern clades such as Skincomarfa, though many Jurassic squamates have unclear relationships to living groups. Ixotisaurus from the late Jurassic of Germany has been suggested to be an early relative of geckos and displays adaptations for climbing. Dorsetosaurus from the late Jurassic of North America and Europe represents the oldest widely accepted record of Anguimorpha. Marmoretta from the Middle Jurassic of Britain has been suggested to represent a late surviving Lepidopteromorph outside both Rhynchocephalia and Squamata, though some studies have recovered it as a stem squamate. Phanerozoic herzogii holotype fossil Phanerozoic herzogii, a Rhynchocephalian from the Upper Jurassic Solnhofen limestone of Germany. Phanerozoic maximiliani, lizard, Jurassic, Solnhofen limestone, Eichstätt, Bavaria, Germany. Houston Museum of Natural Science. Scopomosaurus maximiliani, a Rhynchocephalian from the Solnhofen limestone. Phyllorhizosaurus obchlorosaurus, an aquatic Rhynchocephalian from the late Jurassic of Europe. Phyllioxtotisaurus schroederi Obextotisaurus schroederi, an extinct lizard from the Solnhofen limestone. The time has come to unravel the secrets behind Choristidas and gain a deeper understanding. Lefthumbopriter skeleton of Karoo-Ferrar, the earliest known remains of Choristidra, a group of freshwater aquatic reptiles with uncertain affinities to other reptile groups, are found in the Middle Jurassic. Only two genera of Choristida are known from the Jurassic. One is the small lizard-like Ctenogenes, thought to be the most basal known Choristida. It is known from the Middle to Late Jurassic of Europe and Late Jurassic of North America, with similar remains also known from the Upper Middle Jurassic of Kyrgyzstan and Western Siberia. The other is Karoo-Ferrar from the Late Jurassic of China, which is a more advanced Toarcian, though still small and lizard-like in morphology. In this part of the video, we'll be diving deep into ichthyosaurs and unraveling its profound impact. Ichthyosaurs suffered an evolutionary bottleneck during the end Triassic extinction, with all non-Neotheroians becoming extinct. Ichthyosaurs reached their apex of species diversity during the early Jurassic, with an array of morphologies including the huge apex predator Temidontosaurus and swordfish-like Oinosaurus, though early Jurassic ichthyosaurs were significantly less morphologically diverse than their Triassic counterparts. At the early Middle Jurassic boundary, between the end of the Toarcian and the beginning of the Bogocean, most lineages of ichthyosaur appear to have become extinct, with the first appearance of the Phanerozoic, the clade that would encompass almost all ichthyosaurs from then on. During the early Bogocean, Phanerozoids were diverse by the late Jurassic but failed to fill many of the niches that had been occupied by ichthyosaurs during the early Jurassic. Prepare yourself for an in-depth analysis of plesiosaurs in this section. Plesiosaurs originated at the end of the Triassic Cretaceous. Either end of the Triassic, all other sauropterygians, including planktonts and nothosaurs, had become extinct. At least 6 lineages of plesiosaur crossed the Triassic-Jurassic boundary. Plesiosaurs were already diverse in the earliest Jurassic, with the majority of plesiosaurs in the Hettangian-aged blue layers belonging to the Romuliosauridae. Early plesiosaurs were generally small-bodied, with body size increasing into the Toarcian. There appears to have been a strong turnover around the early Middle Jurassic boundary, with microclidids and Romuliosaurids becoming extinct and nearly extinct respectively after the end of the Toarcian, with the first appearance of the dominant clade of plesiosaurs of the latter half of the Jurassic, the Cryptoclididae, during the Bogocean. The Middle Jurassic saw the evolution of short-necked and large-headed thalassophonan pliosaurs from ancestrally small-headed, long-necked forms. Some thalassophonan pliosaurs, such as some species of Pliosaurus, had skulls up to 2 meters in length with body lengths estimated around meters, making them the apex predators of late Jurassic oceans. Plesiosaurs invaded freshwater environments during the Jurassic, with indeterminate remains of small-bodied plesiosaurs known from freshwater sediments from the Jurassic of China and Australia. As we enter this new phase, let's analyze pterosaurs from different angles and evaluate its significance. Pterosaurs first appeared in the late Triassic. A major radiation of Jurassic pterosaurs is the Mehamphrinchidae, which first appeared in the late early Jurassic Toarcian, that are thought to have been piscivorous. Anorognathids, which first appeared in the Middle Jurassic, possessed short heads and densely furrowed bodies, and are thought to have been insectivores. Derived monophene straton pterosaurs such as Wuconopterids appeared in the late Middle Jurassic. Advanced short-tailed pterodactyloids first appeared at the middle-late Jurassic boundary. Jurassic pterodactyloids include the ctenochasmatids, like Ctenochasma, which have closely spaced needle-like teeth that were presumably used for filter feeding. The bizarre late Jurassic ctenochasmatoid cyanamphus had a jaw with teeth only at the tips, with bent jaws like those of living opendal stalks that may have been used to hold and crush hard invertebrates. As we enter this new phase, let's navigate the complexities of dinosaurs and discover its practical applications. Dinosaurs, which had morphologically diversified in the late Triassic, experienced a major increase in diversity and abundance during the early Jurassic in the aftermath of the end Triassic extinction and the extinction of other reptile groups, becoming the dominant vertebrates in terrestrial ecosystems. Chiosaurus, a morphologically aberrant herbivorous dinosaur from the late Jurassic of South America, has uncertain relationships to the 3 main groups of dinosaurs, having been recovered as a member of all 3 in different analyses. Prepare yourself for an in-depth analysis of theropods in this section. Advanced theropods belonging to Notheropods first appeared in the late Triassic. Basal Notheropods, such as Coelophysoids and Dilophosaurs, persisted into the early Jurassic, but became extinct by the Middle Jurassic. The earliest of restaurants appeared during the early Jurassic, with the earliest known member of Ceratosauria being Saltriaventa from the early Silurian million years ago of Italy. The unusual Ceratosauria from the late Jurassic of China had a herbivorous diet, with adults having edentulous-beaked jaws, making it the earliest known theropod to have converted from an ancestrally carnivorous diet. The earliest members of the Tetanura appeared during the late early Jurassic or early middle Jurassic. The Megalosauриdae represent the oldest radiation of the Tetanura, first appearing in Europe during the Bogeocean. The oldest member of Allosaurida has been suggested to be Asphaltovenata from the Middle Jurassic of South America. Coelurosaurs first appeared during the Middle Jurassic, including early tyrannosaurs such as Proceratosaurus from the Barthenian of Britain. Some coelurosaurs from the late Jurassic of China, including Shishiganicus and Hapakyrus, are suggested to represent early alvarezos. However, this has been questioned. Sconsauripterygids, a group of small feathered coelurosaurs with membranous, bat-like wings for gliding, are known from the Middle to late Jurassic of China. The oldest record of troodontids is suggested to be Hesperornithoides from the late Jurassic of North America. Tooth remains suggested to represent those of dromaeosaurs are known from the Jurassic, but no body remains are known until the Cretaceous. Phanerozoic mounted white backgrounded skeleton of Ceratosaurus, a ceratosaurid from the late Jurassic of North America. Phanerozoic geologic skeleton of Menolophosaurus, a basal titanoran from the Middle Jurassic of China. Phyloiki restoration of Yiki, a Sconsauripterygid from the Middle to late Jurassic of China. Get ready to uncover the mysteries surrounding birds as we navigate its intriguing terrain. The earliest aviolans, which include birds and their ancestors, appeared during the Middle to late Jurassic, definitively represented by Archaeopteryx from the late Jurassic of Germany. Aviolans belong to the clade paras within Coelurosauria, which also includes dromaeosaurs and troodontids. The Anchiornithidae from the Middle Late Jurassic of Eurasia have frequently suggested to be aviolans, but have also alternatively found as a separate lineage of Pervians. In this part of the video, we'll be delving deeper into ornithischians and analyzing its key components. The earliest definitive ornithischians appeared during the early Jurassic, represented by basal ornithischians like Lesothosaurus, Heterodontosaurids, and early members of Thyreophora. The earliest members of Ankylosauria and Stegosauria appeared during the Middle Jurassic. The basal Neanderthalian Coelentodromeus from the Middle Jurassic of Russia indicates that at least some ornithischians were covered in protofeathers. The earliest members of Ankylopalexia, which become prominent in the Cretaceous, appeared during the late Jurassic, represented by bipedal forms such as Camptosaurus. Ceratopsians first appeared in the late Jurassic of China, represented by members of Chiangsauridae. In this section, we'll be peeling back the layers of sauropodomorphs to reveal its true essence. Sauropods became the dominant large herbivores in terrestrial ecosystems during the Jurassic. Some Jurassic sauropods reached gigantic sizes, becoming the largest organisms to have ever lived on land. Basal bipedal sauropodomorphs, such as marsuspondyllids, continued to exist into the early Jurassic, but became extinct by the beginning of the Middle Jurassic. Quadrupedal sauropomorphs appeared during the late Triassic. The quadrupedal Ledumhodi from the earliest Jurassic of South Africa reached an estimated weight of 12 tons, far in excess of other known basal sauropodomorphs. Gravisaurian sauropods first appeared during the early Jurassic, with the oldest definitive record being Vulcanodon from Zimbabwe, likely of Silurian age. Eusauropods first appeared during the late early Jurassic Toarcian and diversified during the Middle Jurassic. These included Cetiosaurids, Turiasaurs, and Rhynchosaurs. Neuropods such as Macronorians and Diplodocids first appeared during the Middle Jurassic, before becoming abundant and globally distributed during the late Jurassic. As we transition, let's shed light on amphibians and its relevance to our ongoing exploration. The diversity of temnospondyls had progressively declined through the late Triassic, with only brachiopods surviving into the Jurassic and beyond. Members of the family Brachiopidae are known from Jurassic deposits in Asia, while the Chigotosaurid Sidrops is known from the early Jurassic of Australia. Modern lissamphibians began to diversify during the Jurassic. The early Jurassic Procellaris thought to represent the first frog relative with a morphology capable of hopping like living frogs. Morphologically recognizable stem frogs like the South American Notobatrachus are known from the Middle Jurassic, with modern crown group frogs like Enobatrachus and Reginistus appearing by the late Jurassic, while the earliest salamander line amphibians are known from the Triassic. Crown group salamanders first appeared during the Middle to Late Jurassic in Eurasia, alongside stem group relatives. Many Jurassic stem group salamanders, such as Marmopaton and Cocytus, are thought to have been neotenic. Early representatives of crown group salamanders include Tunapaton, Pangopaton, and Lingontriton from the Middle to Late Jurassic Yanli biota of China. Some of these are suggested to belong to Cryptobranchoia, which contains living Asiatic and giant salamanders. Ionopaton and Kingontriton from the same biota are thought to be early members of Salamandroia, the group which contains all other living salamanders. Salamanders dispersed into North America by the end of the Jurassic, as evidenced by Eriotriton, found in the late Jurassic Morrison Formation. The stem Caecilian Eocacilia is known from the early Jurassic of Arizona. The fourth group of lissamphibians, the extinct salamander-like Albinopatentids, first appeared in the Middle Jurassic, represented by Anulopaton priscus from the Balfinian of Britain, as well as indeterminate remains from equivalently aged sediments in France and the Anule Formation of Morocco. With that being said, let's now move on to mammaliformes. Mammaliformes, including mammals, having originated from cynodonts at the end of the Triassic, diversified extensively during the Jurassic. While most Jurassic mammaliforms are solely known from isolated teeth and jaw fragments, exceptionally preserved remains have revealed a variety of lifestyles. The Dodontan Castarchida was adapted to aquatic life, similarly to the platypus and otters. Some members of Haramida and the Utriconodontan tribe Volaticotherini had a patagem akin to those of flying squirrels, allowing them to glide through the air. The aardvark-like mammal Frutifossa, of uncertain taxonomy, was likely a specialist on colonial insects, similarly to living anteaters. Astrolosphenida, a group of mammals possibly related to living monotremes, first appeared in the Middle Jurassic of Gondwana. The earliest records of multituberculates, of the longest-lasting and most successful orders of mammals, are known from the Middle Jurassic. Therian mammals, represented today by living placentals and marsupials, diversified meteorically during the Middle Jurassic. They have their earliest records during the early Late Jurassic, represented by Juramaea, a Eutherian mammal closer to the ancestry of placentals than marsupials. Juramaea is much more advanced than expected for its age, as other Therian mammals are not known until the early Cretaceous, and it has been suggested that Juramaea may also originate from the early Cretaceous instead. Two groups of non-mammaliform cynodonts persisted beyond the end of the Triassic. The Insectivirus Trivaldon today has a few records from the early Jurassic. The Tritylodontidae, a herbivorous group of cynodonts that first appeared during the Haitian, has abundant records from the Jurassic, overwhelmingly from the Northern Hemisphere. In the upcoming section, we'll be dissecting Eoless fish and exploring its implications in greater detail. The last known species of Canodont, a class of Eoless fish whose hard, tooth-like elements are key index fossils, finally became extinct during the earliest Jurassic after over 300 million years of evolutionary history, with an asynchronous extinction occurring first in the Tethys and eastern Panthalassa and survivors persisting into the earliest Hetengian of Hungary and central Panthalassa. End-Triassic Canodonts were represented by only a handful of species and have been progressively declining through the Middle and Late Triassic. Yanliamizon from the Middle Jurassic of China represents the oldest post-Paleozoic lamprey, and the oldest lamprey to have the toothed feeding apparatus and likely the three-stage life cycle typical of modern members of the group. Let's transition to Sarcopterygi and uncover its significance. Lungfish definitely were present in freshwater environments of both hemispheres during the Jurassic. Some studies have proposed that the last common ancestor of all living lungfish lived during the Jurassic. Morsaniids, a marine and freshwater brackish group of coelacanths which first appeared in North America during the Triassic, expanded into Europe and South America by the end of the Jurassic. The marine Latimeriidae, which contains the living coelacanths of the genus Latimeria, were also present in the Jurassic, having originated in the Triassic, with a number of records from the Jurassic of Europe including Swinsia, thought to be the closest known relative of living coelacanths. With the groundwork laid, let's now examine actiniturgy and its connections to our previous discussions. Thumboprita fossil of Triceps, an ichthydictid stem group tellus from the late Jurassic Solnhofen limestone of Germany, showing preserved coloration ray finnid fish. Actiniturgy were major components of Jurassic freshwater and marine ecosystems. Archaic paleoniscid fish, which were common in both marine and freshwater habitats during the preceding Triassic, declined during the Jurassic, being largely replaced by more derived actiniturgian lineages. The oldest known Acipenseriformes, the group that contains living sturgeon and paddlefish, are from the early Jurassic. Amethum fish, which today only includes the bowfin, first appeared during the early Jurassic, represented by Catharus from the Plians Achaean of Britain. After their appearance in the western Tethys, they expanded to Africa, North America and Southeast and East Asia by the end of the Jurassic, with the modern family Amidae appearing during the late Jurassic. Pycnodontiformes, which first appeared in the western Tethys during the late Triassic, expanded to South America and Southeast Asia by the end of the Jurassic, having a high diversity in Europe during the late Jurassic. During the Jurassic, the Gymnodontidae, the only living representatives being gars lepicistidae, were diverse in both freshwater and marine environments. The oldest known representatives of anatomically modern gars appeared during the late Jurassic. Stem group telosts, which make up over 99% of living actiniturgy, had first appeared during the Triassic in the western Tethys. They underwent a major diversification beginning in the late Jurassic, with early representatives of modern telost clades such as Elopomorpha and Ostoglossoides appearing during this time. The Pachycomiformes, a group of marine stem telosts, first appeared in the early Jurassic and included both tuna-like predatory and filter-feeding forms. The latter included the largest bony fish known to have existed, Leedsichthys, with an estimated maximum length of over 15 meters, known from the late Middle to late Jurassic. Moving on to the next segment, we have Chondrichthyes. Thumboprita fossil of Palocarcharias, the oldest known lamethum shackled fossil of a shark preserved in bottom-up view during the early Jurassic, the shark-like hybridants, which represented the dominant group of chondrichthyans during the preceding Triassic, were common in both marine and freshwater settings. However, by the late Jurassic, hybridants had become minor components of most marine communities, having been largely replaced by modern neozoologians, but remained common in freshwater and restricted marine environments. The neozoology, which contains all living sharks and rays, radiated beginning in the early Jurassic. The oldest known ray betoia is Anticoibatis from the Plians Achaean of Germany. Jurassic betoids known from complete remains retain a conservative, wheaterfish-like morphology. The oldest known Exantiformes and carpet sharks or Ectolobiformes are from the early Jurassic Plians Bacchian and Toarcian, respectively, of Europe. The oldest known members of the Heterodontiformes, the only living members of which are the bullhead shark Heterodontus, first appeared in the early Jurassic, with representatives of the living genus appearing during the late Jurassic. The oldest known mackerel sharks Lammiformes are from the Middle Jurassic, represented by the genus Palocarcharias, which has an Orectolobiform-like body but shares key similarities in tooth histology with Lammiformes, including the absence of orthodontin. The oldest record of angel sharks, Stratiniformes, is Pseudorina from the late Jurassic Oxfordian Tithinian of Europe, which already has a body form similar to members of the only living genus of the order, Stratina. The oldest known remains of Carchariniformes, the largest order of living sharks, first appear in the late Middle Jurassic Barthenian of the western Tethys, England and Morocco. Known dental and exceptionally preserved body remains of Jurassic Carchariniformes are similar to those of living cacharks. Cynecodontiformes, an extinct group of sharks closely related to Neozoici, were also widespread during the Jurassic. The oldest remains of modern chimeras are from the early Jurassic of Europe, with members of the living family Calorhynchidae appearing during the Middle Jurassic. Unlike most living chimeras, Jurassic chimeras are often found in shallow water environments. The closely related Swallowjaw and Myriacanthoids are also known from the Jurassic of Europe. Now, we shift our focus to insects and arachnids, a topic that deserves our attention. There appears to have been no major extinction of insects at the Triassic-Jurassic boundary. Many important insect fossil localities are known from the Jurassic of Eurasia, the most important being the Carbuster Formation of Kazakhstan and the various Yanli biota deposits in Inner Mongolia, China, such as the Dahigo bed, dating to the Calovia Oxfordian. The diversity of insects stagnated throughout the early and middle Jurassic, but during the latter third of the Jurassic regeneration rates increased substantially while extinction rates remained flat. The increasing diversity of insects in the mid-late Jurassic corresponds with a substantial increase in the diversity of insect mouthparts. The middle to late Jurassic was a time of major diversification for beetles, particularly for the Subida polyvida, which represents 90% of living beetle species but which was rare during the preceding Triassic. Weevils first appear in the fossil record during the middle to late Jurassic, but are suspected to have originated during the late Triassic to early Jurassic. Orthopteran diversity had declined during the late Triassic, but recovered during the early Jurassic, with the Hagloia, a superfamily of ensiferan orthopterans today confined to a few living species, being particularly diverse during the Jurassic. The oldest known lepidopterans, the group containing butterflies and moths, are known from the Triassic-Jurassic boundary, with wing scales belonging to the Subidodocita and Micropterigidae grade moths from the deposits of this age in Germany. Modern representatives of both dragon fleas and damsel fleas also first appeared during the Jurassic. Although modern representatives are not known until the Cenozoic, ectoparasitic insects thought to represent primitive fleas, belonging to the family Pseudoglycidae, are known from the Middle Jurassic of Asia. These insects are substantially different from modern fleas, lacking the specialist morphology of the latter and being larger. Parasitoid wasps Apocrita first appeared during the early Jurassic and subsequently became widespread, reshaping terrestrial food webs. The Jurassic also saw the first appearances of several other groups of insects, including Phasmatodous stick insects, Mantophasmatidae gladiators, Embioptera web spinners, and Raphidioptera snake fleas. The earliest scale insect Coccomarpha is known from amber dating to the late Jurassic, though the group probably originated earlier during the Triassic. Only a handful of records of mites are known from the Jurassic, including Jormus, an oribated mite belonging to the family Cymboremedae known from the late Jurassic of Britain and Russia, and a member of the still-living orbated genus Hydrositis from the early Jurassic of Sweden. Spiders diversified through the Jurassic. The early Jurassic Cephalocoponini may represent a stem group to Palpimenoida. Oplectries from the Middle Jurassic of China is considered a stem lineage of Cinspermata. The oldest member of the family Archeidae, Patacho, is known from the Middle Jurassic of China. Mongol archon from the Middle Jurassic of China is among the largest known fossil spiders, with legs over 5 centimeters longitude. The only scorpion known from the Jurassic is Lysa scorpionides from the early Jurassic of Germany, of uncertain placement. Eugnoi harvestmen opilions are known from the Middle Jurassic of China, including members of the family Sclerosomatidae. Let's now enter the realm of end-Triassic extinction and discover the fascinating stories it has to tell. During the end-Triassic extinction, % of all marine genera became extinct. The effects of the end-Triassic extinction were greatest at tropical latitudes and were more severe in Panthalus than the Tethys or Boreal oceans. Tropical reef ecosystems collapsed during the event, and would not fully recover until much later in the Jurassic. Sessile filter feeders and photosymbiotic organisms were among those most severely affected. The spotlight now falls on marine ecosystems as we delve deeper into its details. Having declined at the Triassic-Jurassic boundary, Reefs substantially expanded during the late Jurassic, including both sponge reefs and scaratinian coral reefs. Late Jurassic reefs were similar in form to modern reefs but had more microbial carbonates and hypercalcified sponges, and had weak begonic binding. Reefs sharply declined at the close of the Jurassic, which caused an associated drop in diversity in decapod crustaceans. The earliest planktonic foraminifera, which constitute the Pseudoglobigerina, are known from the late early Jurassic mid-torsion of the western Tethys, expanding across the whole Tethys by the Middle Jurassic and becoming globally distributed in tropical latitudes by the late Jurassic. Coccolithophores and dinoflagellates, which had first appeared during the Triassic, radiated during the early to Middle Jurassic, becoming prominent members of the phytoplankton. Microconchid tube worms, the last remaining order of Tentaculata, a group of animals of uncertain affinities that were convergent on Spirorbis tube worms, were rare after the Triassic and had become reduced to the single genus Punctoconchus, which became extinct in the late Barthenian. The oldest known diatom is from late Jurassic aged amber from Thailand, assigned to the living genus Hemilus. With the foundation laid, let's embark on a journey into echinoderms. Crenids diversified throughout the Jurassic, reaching their peak Mesozoic diversity during the late Jurassic, primarily due to the radiation of sessile forms belonging to the orders Cetacrinida and Milleracrinida. Echinids sea urchins underwent substantial diversification beginning in the early Jurassic, primarily driven by the radiation of irregular asymmetrical forms, which were adapting to deposit feeding. Rates of diversification sharply dropped during the late Jurassic. Now, let's shift our perspective and explore crustaceans through a fresh lens, unlocking new perspectives. The Jurassic was a significant time for the evolution of decapods. The first true crabs Brachyura are known from the early Jurassic, with the earliest being E. Carcinis precursor from the early Plians Bacchian of England, which lacked the crab-like morphology carcinisation of modern crabs, and E. Precipitantus from the late Plians Bacchian of Germany, which may belong to the living family Homolodromiidae. Most Jurassic crabs are known only from carapace pieces, which makes it difficult to determine their relationships. While rare in the early and middle Jurassic, crabs became abundant during the late Jurassic as they expanded from their ancestral silty seafloor habitat into hard substrate habitats like reefs, with crevices in reefs providing refuge from predators. Hermit crabs also first appeared during the Jurassic, with the earliest known being Schobotella holderi from the late Hettangian of Germany. Early hermit crabs are associated with ammonite shells rather than those of gastropods. Glyphides, which today are only known from 2 species, reached their peak diversity during the Jurassic, with around 150 species out of a total fossil record of 250 known from the period. Jurassic barnacles were of low diversity compared to present, but several important evolutionary innovations are known, including the first appearances of calcite-shelled forms and species with an epiplanktonic mode of life. Turning our focus to brachiopods, let's explore its key elements. Brachiopod diversity declined during the Triassic-Jurassic extinction. Spire-bearing brachiopods, Spirophrenida and Archaeidida did not recover their biodiversity, becoming extinct in the TOAE. Rhynchonellida and Tuberculida also declined during the Triassic-Jurassic extinction but rebounded during the early Jurassic. Neither clade underwent much morphological variation. Brachiopods substantially declined in the late Jurassic. The causes are poorly understood. Proposed reasons include increased predation, competition with bivalves, enhanced butybation or increased grazing pressure. As we enter this new phase, let's navigate the complexities of bryozoans and discover its practical applications. Like the preceding Triassic, bryozoan diversity was relatively low compared to the Paleozoic. The vast majority of Jurassic bryozoans are members of Cyclostomatida, which experienced irradiation during the Middle Jurassic, with all Jurassic representatives belonging to the Subidas Tubuloparina and Seriparina. Coelostomata, the dominant group of modern bryozoans, first appeared during the late Jurassic. With our foundation established, It's time to explore gastropods and its relevance to our overarching theme. Marine gastropods were significantly affected by the TJ extinction, with around 56% of genera going extinct, with Neratomorpha being particularly strongly affected, while Heterobranchia suffered much lower losses than other groups. While present, the diversity of freshwater and land snails was much lower during the Jurassic than in contemporary ecosystems, with the diversity of these groups not reaching levels comparable to modern times until the following Cretaceous. As we enter this new chapter, let's navigate the complexities of bivalves and unravel its multifaceted nature. The end Triassic extinction had a severe impact on bivalve diversity, though it had little impact on bivalve ecological diversity. The extinction was selective, having less of an impact on deep burrows, but there is no evidence of a differential impact between surface-living epifaunal and burrowing-in faunal bivalves. Bivalve family-level diversity after the early Jurassic was static, though genus diversity experienced a gradual increase throughout the period. Rudists, the dominant reef-building organisms of the Cretaceous, first appeared in the late Jurassic mid-Oxfordian in the northern margin of the western Tethys, expanding to the eastern Tethys by the end of the Jurassic. As we venture forward, let's take a closer look at cephalopods and its impact on our understanding. Ammonites were devastated by the end Triassic extinction, with only a handful of genera belonging to the family Psiloceratidae of the Subidophylloceratina surviving and becoming ancestral to all later Jurassic and Cretaceous ammonites. Ammonites explosively diversified during the early Jurassic, with the orders Psiloceratina, Ammonitina, Litoceratina, Haploceratina, Prosphinctina and Anciloceratina all appearing during the Jurassic. Ammonite faunas during the Jurassic were regional, being divided into around 20 distinguishable provinces and subprovinces in two realms: the northern high-latitude Panboral realm, consisting of the Arctic, northern Panthalassa and northern Atlantic regions, and the equatorial southern Pantethyan realm, which included the Tethys and most of Panthalassa. Ammonite diversifications occurred covalently with marine transgressions, while their diversity natters occurred during marine regressions. The oldest definitive records of the squid-like belemnites are from the earliest Jurassic hetangians in Merion of Europe and Japan. They expanded worldwide during the Jurassic. Belemnites were shallow water dwellers, inhabiting the upper 200 meters of the water column on the continental shelves and in the littoral zone. They were key components of Jurassic ecosystems, both as predators and prey, as evidenced by the abundance of belemnite guards in Jurassic rocks. The earliest vampiromorphs, of which the only living member is the vampire squid, first appeared during the early Jurassic. The earliest octopuses appeared during the Middle Jurassic, having split from their closest living relatives, the vampiromorphs, during the Triassic to early Jurassic. All Jurassic octopuses are solely known from the hard Gladius. Octopuses likely originated from bottom-dwelling benthic ancestors which lived in shallow environments. Proto-octopus from the late Middle Jurassic Lovaltsoven Lagostat, previously interpreted as an early octopus, is now thought to be a basal taxon outside the clade containing vampiromorphs and octopuses. I love interacting with my viewers, so leave me a comment and I'll do my best to respond.